In this lecture, we are going to discuss about the numerical part 5 in a electrical machines. A 10 kilowatt 400 volts 4-pole delta connected induction motor gave the following test results. No load test 400 volts 8 amperes 250 watts. Block rotor test 90 volts 25 amperes 1350 watts. The DC resistance of stator winding is measured immediately after the block rotor test is 0.6 ohm. Calculate the rotation losses and equivalent parameters of induction motor. This is a numerical which is based upon the node block rotor test of a induction motor. So first of all, you have to calculate the rotation loss. So to calculate the rotation losses, when you're conducting a no-load test in induction motor, how much power is taken by the induction motor? That is meeting the stator copper loss, stator core loss, and the windage and section loss. From this value, if you subtract the stator copper loss, then it gives the rotation loss. So whatever the power is taken by the induction motor during no test, that is 250 watts, it is going to meet the stator copper loss and the rotation loss. So from this input power, if you subtract the stator copper loss, that is, it gives the rotation loss. So no load rotation loss is equal to no load power minus stator copper loss. So that is denoted by P suffix R. This is equal to 250 minus 3 into the per phase current taken by the induction motor due to the no load because it is delta connected. 8 amperes of current is taken, so 8 by root 3 into whole square into resistance of a stator winding. This is the DC resistance into 1.2 gives the AC resistance. Simplify this one, we are getting a 203.92 watts. Now we are going to find out the equivalent parameters of induction motor. From the no load test, the per phase no load impedance ZNL equal to per phase no load voltage divided by the per phase no load current. So it is delta connected. So line voltage equal to phase voltage 400 by 8 by root 3. If you simplify this one 86.6 ohms. So per phase no load resistance equal to R suffix NL equal to per phase power divided by the per phase current square. So this is equal to 250 by 3 into 8 by root 3 whole square. We are getting the 3.91 ohm. Per phase no load reactance equal XNL equal to square root of ZNL square minus RNL square. This is equal to square root of 86.6 whole square minus 3.91 whole square. We are getting the 86.51 ohm. Now from a block rotor test, per phase block rotor impedance equal to block voltage divided by the per phase block rotor current. So 90 by 25 by root 3 whole square, we are getting a 4.454 ohm. So per phase block rotor resistance equal to per phase block rotor power divided by the per phase block rotor current square. So this is the total power divided by 3 gives the per phase power 25 by root 3 whole square, which gives the 1.102 ohm. So per phase block rotor impedance XBR equal to square root of ZBR minus RBR square. Substitute all the values, you are getting the 4.316. XBR equal to stator leakage reactance plus rotor leakage reactance with respect to the stator. This is equal to 4.316. But practically these two values are equal. So XS equal to XR dash equal to 4.316 by 2. You are getting the 2.156. Now we got the two values. Now from the magnetization reactance, XM equal to XNL minus XS. So XNL value from the no load test we got this one. This is 86.51 minus 2.156. We are getting that. Here we got the value of XS to substitute here. We are getting the 84.35. Now rotor self reactance X2 equal to XM plus XR dash. Substitute all the values. We are getting the 86.51 ohms. From a block rotor test, we know the one formula for the rotor resistance. Per phase rotor resistance R2 equal to RBR minus RS into X2 by XM whole square, where X2 is nothing but a rotor self reactance. Already we calculated this value. Substitute all the values. We are getting the 0.402 ohm. Thus, the parameters of induction motor are RS equal to 0.72 ohm, R2 equal to 0.42 ohm, XS equal to XR dash equal to 2.158 ohm. Magnetization reactance equal to 84.352 ohm. So in this manner, we can calculate the parameters of induction motor from the no load on block rotor test data. Now come to the next numerical. A three-phase star connector 400 volts 50 Hz 4-pole induction motor has the following per phase parameters referred to the status is given. RS equal to 0.15 ohm, XS equal to 0.45 ohm, R2 equal to 0.12 ohm, X2 equal to 0.45 ohm. Magnetization reactance equal to 28.5 ohm. Fixed losses are given 400 volt. Compute the stator current, rotor speed, output torque, efficiency when the motor is operating at a slip of 4%. So this is the equivalent circuit of induction motor. What are the parameters are given in a numerical? All those parameters we inserted in this equivalent circuit. This is stator resistance. This is the stator leakage reactance. This is the rotor leakage reactance. This is the R2 dash by S. This is the magnetization reactance. This is the per phase voltage. This induction motor is connected in a star. What is the voltage given here? 400 volts. That is the line voltage. So per phase voltage becomes 405. Now we have to find out the source current. That how much current is passing in this circuit when the slip of the induction motor is 4%. These two branches in parallel, that is series with this branch, which gives the equivalent impedance between the AB, that we have taken as a ZAB. So ZAB equal to RS plus JXS plus JXM into R2 by S plus JX2 whole divided by R2 plus JX2 plus XM, because these two in parallel we got this term. Now this term we can write it as a real term plus J reactive term. Now substitute all the values which are given in the numerical. If you simplify that one, so finally you're getting the equivalent impedance ZAB equal to 3.25 at angle 21.47 degrees. See here, RF is nothing but a, see, this is the resistance component in rotor circuit. So RF equal to 2.87, this component. Now stator current equal to per phase voltage divided by the impedance. So 400 at angle 0 divided by root 3 gives the per phase voltage. Already we calculated this value, that is the impedance between the A and B, 3.25 at angle 21.47. Finally, we are getting the 71.46 at angle minus 21. The power factor equal to cos of minus 21.4 degrees. We are getting the 0.93 lakh. Stator input power. The stator input power equal to root 3 VL IL cos phi. We know the VL IL also we calculated here. So take all these values, we are getting the 45.784 kilowatt. A gap power is nothing but what are the power is wasted across RF. That power is nothing but air gap power. So air gap power equal to 3 into I1 square into RF. Why I have taken the 3 means this is 3-phase induction motor. So 3 into 71.46 square into 2.87, you are getting the 43.476 kilowatts. Synchronous speed equal to 120 F by P. Substitute all the values, you are getting the 1500 RPM. Now speed of an induction motor is given, that is N equal to 1440 RPM. Now the synchronous speed in radians per second, that is equal to 2 pi ns by 60, you are getting the 55 radians per second. The mechanical power developed Pm equal to 1 minus S into rotor input. The rotor input is nothing but a air gap power. Already we calculated this value. You take that value, you are getting a 41.737 kilowatt. The power output, nothing but shaft power equal to mechanical power developed minus windage and friction losses. So 41.734 minus windage and friction loss also given in the numerical. You take that value, you are getting a 41.327 kilowatt. Shaft torque equal to the power which is available at the shaft divided by the angular speed of a shaft, that is omega r. Now you take this value, shaft power is nothing but 41.337 kilowatt, that you convert into watt, divided by 1 minus S into omega s. Omega r equal to 1 minus S into omega s. You take that value here, substitute all the values, finally you are getting the 273.12 Newton meter. Various losses occurs in induction motor, that is equal to stator copper loss equal to 3 into IS square RF. So this is equal to 3 into 71.064 square into 0.15. IS already we calculated, that is phase current equal to line current only, because it is star connected. We take that value. RS value also given 0.15, substitute all the values, we are getting the 2272.3 watts. Rotor ohmic losses equal to S into air gap power. So this is equal to 0.04 into air gap power. Already we have calculated that is 43,476. We are getting the 1,739 watts. So fixed losses are given, that is 400 watts. If we add all these components, I think the total losses occurs in the induction motor, that is we are getting the 4,411.3 watts. Now the shaft power equal to, already we calculated the shaft power, that is 41.337 watts. The power input equal to shaft power plus total losses occurs in an induction motor, that is this plus these losses, we are getting the 45.746. Now the efficiency of induction motor equal to 1 minus losses divided by the input power of the induction motor, that is equal to 1 minus 4.411 divided by 45.748. Earlier getting a 90.36%. So in this manner, from the equivalent circuit also we can calculate the what are the different parameters of induction motor for given values suppose induction motor. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of the YouTube channel, so that I'm always welcome to answer all your